Hi there, folks. This is the practice chapter 6 test, and as always, I am the amazing Mr. Jansen, so away we go. If we look at the first one, we're just simply doing the square root here, and I want the negative version of the square root, so this one's going to be a -9. For number 2, when we're dealing with fractions here, we have to take the square root of each of these individually, so the square root of the numerator is a 3, the square root of the denominator is a 4, so it's 3/4, but it's a plus or minus 3/4 because there was a plus or minus out front. And that's it. If we take a look at the next one, we want to know which of the following requires the absolute value around the answer, okay? Remember, when we're doing absolute value, when we're doing roots and exponents, we need absolute value when we have an even root. So right away, these two don't require absolute value, okay? Because the cube root can be negative, so we don't need to make sure it's positive, okay? So now it's down to these two. And only one of these requires absolute value. And technically, when I take the square root of something, I need the absolute value. But in this case, if I put absolute value around this one, that's the one that needs it because x cubed can be negative, but x to the 6th is going to be positive all on its own. So it doesn't need the absolute value. Even though I would have put the absolute value, I'd find out that that's redundant because x to the 6th is already going to be positive no matter what. Okay? So the answer here is letter A. For the next couple, we're going to simplify, and we're going to assume that all the variables are positive, so don't have to worry about this absolute value thing. So let's prove that we can do it number 3, and now we're going to kind of ignore that rule for the moment. All right. For this first one, I'm looking for perfect squares that divide evenly into 48. Breaks down into a 16 times 3. And now the square root of 16 is a 4. The 4 goes to the outside. It's a changed number on the outside. It's learning from his mistakes, but the 3 is still trapped. Okay. So you got to be perfect to get out of there, and once you're out, you're different. Okay. You're not the same number you were when you were inside the radical. If I take the square root of 98, I can break that down into a 49 times 2. The square root of 49 is a 7. It's a changed number on the outside. The 2 is still trapped. If I look at number 6 here, I'm looking for perfect squares that divide evenly into 27. It's going to be a 9 times a 3. And now in terms of the variables, in terms of exponents, I need exponents that are divisible by 2. Because remember, when I take the root, I actually divide the exponents. So I'm going to break this down into x to the 4th times x. Y to the 10th is already a perfect square because it's got an exponent that's divisible by 2. So now the square root of 9 is a 3. The square root of x to the 4th is x to the 2nd. The square root of y to the 10th is y to the 5th. And again, we're assuming all variables are positive, so I don't need my absolute value around that. And now underneath here, I still have the 3 and the x left over. Okay? Number 7, we're doing the same thing. I got to break this down into perfect squares. And again, try to find the largest perfect squares possible. For 72, it's a 36 times 2. And now again, with the variables, I need exponents that are divisible by 2, so I'm going to break this one down into x to the 10th times x. The y to the 2nd is already perfect. The z to the 2nd is also already perfect, so I'm going to leave it the way it is. Now I take the square root of each. The square root of 36 is a 6, as I tried to write a 3. The square root of x to the 10th is x to the 5th. The square root of y to the 2nd is y. The square root of z to the 6th is z to the 3rd. And really, in this particular example, all of these would need absolute value, but we're ignoring that for right now. It's just a 2x left underneath. Okay? For this one, this time it's a cube root. With square roots, we were looking for perfect squares. With cube roots, we're looking for perfect cubes. So any perfect cubes that divide evenly into 54 looks like a 27 times 2. And now for the variables, just like with a square root, I needed exponents that were divisible by 2. With a cube root, I need exponents that are divisible by 3. So I'm going to break this into x to the 9th times x to the 2nd. This is y to the 15th is already a perfect cube because it's divisible by 3. And then z to the 6th is fine just the way it is as well. So now I take the cube root of each. The cube root of 27 is a 3. Okay, because 3 to the 3rd power equals 27. We're undoing that. The cube root of x to the 9th, I divide the exponents. It's going to be an x to the 3rd. The cube root of y to the 15th is y to the 5th. Again, I'm dividing by 3. The cube root of z to the 6th is z to the 2nd. And now still left under my cube root, and keep in mind that this is a cube root, the cube root of 2x squared. Okay? And number 9, if I want to subtract radical terms, I need like radical terms. And I don't have that right now. To have like radical terms, I need the same radical symbol with the same radicand, okay? So the same root with the same number underneath. So what I'm going to do is I'm going to simplify everything as far as I can first and see what I'm left with. So 45, that's going to be a 9 times 5. The square root of 9 is a 3, so it becomes 3 root 5. And now I look at what I have left. Well, neither of these is like radical terms, so I leave it the way it is. It's simplified as far as it can be simplified because I can't combine anything else. Okay? And number 10, I do the same thing. I don't have any like radical terms, so I'm going to simplify everything to see if I can get some like radical terms. So here I've got 4 times 7. This one I can't break down, the 6 stays the way it is. The square root of 24 I can break down into 4 times 6. And now I start taking the square root. The square root of 4 is a 2. It goes to the outside and it multiplies. So again, what's happening here, if I draw a little thought bubble, you should be able to do this in your head, but just in case, that 2 is already out here. Another 2 comes out from taking the square root of 4. And then I multiply those, so it gives me a 4 root 7 out here. Okay? The 3 root 6 stays the way it is. Over here, I do the same thing. The square root of 4 is a 2. And if I create another little thought bubble here, again, what's happening is there was a 5 out here. Now a 2 comes out, root 6. And again, those things on the outside, they multiply. That's going to be minus 10 root 6. And now I look to see if I have any like radical terms. I don't know why I put a multiplication symbol in here like a crazy person. That's a plus sign. But now I have some like radical terms. The root 6's are like radical terms, so the 4 root 7 is not a like radical term with either. Is easy to stay the way it is. But now if I have a 3 root 6 minus a 10 root 6, that's a negative 7 root 6. And again, we kind of treat it like variables in that we subtract or add the coefficients and the radical part stays the same. Okay? In number 11, here we're multiplying. So whenever we're multiplying two binomials, I want to use my distributive property or FOIL. So I'm going to distribute to 3. When I distribute to 3, 3 times 4 is a 12. And now here, when I do 3 times the square root of 2, remember, it's stuff on the outside times stuff on the outside, stuff on the inside, stuff times stuff on the inside. So the 3 and the 2 can't multiply, because one's inside, one's outside. But it's like there's a 1 out front here, so I can do the 3 times the 1, which is a 3. And then the root 2 doesn't change because there's nothing to multiply it with. Okay? So inside times inside, outside times outside. Same thing here. When I distribute the negative root 5, I'm going to multiply it by the 4. It becomes a negative 4 root 5. That 4 has to stay on the outside. The 5 has to stay on the inside. They can't really associate. Okay? So we got to keep them separate. And then the negative root 5 times the root 2. Now each of these is inside the radical, so I can multiply them. It's going to be a negative root 5 times 2, which is 10. Okay? Stuff on the inside with stuff on the inside, stuff on the outside with stuff on the outside. And then I look to see, can I reduce anything here? Are there any radicals that can be simplified? I can't simplify any of these radicals. So now I look to see if I have any like radical terms, and I don't have any like radical terms, so that's it. That's my answer. Okay? If I look at something like number 12, again, I'm going to use my distributive property. So I'm distributing this root 3. So root 3 times root 7, they're both under the square root, so it's a square root of 21. They're allowed to be multiplied because they're both inside the square root. And then the root 3 times the negative root x is a negative root 3x. Again, each of those is inside the radical, so they multiply. And now I distribute the root x. Root x times the root 7, it's going to be a plus root 7x. And then the root x times the negative root x is going to be a negative root. Again, they're each inside here, so I multiply them x squared. Okay? And now I simplify everything as far as I can right here. The square root of x squared is an x. So I've got root 21 minus the square root of 3x plus the square root of 7x minus x. Again, I'm assuming all variables are positive. And now I look through. There's nothing else that can be simplified. I don't have any like radical terms. Don't be fooled by these guys. They don't have the same thing underneath the radical. Yeah, I know that a 3x and a 7x are like terms when they're outside of a radical, but inside a radical we need the exact same thing. So these are not like terms, not like radical terms anyway. So that's it. That's all I can do here. If I look at this one, I want to rationalize the denominator. In order to rationalize the denominator here, I have to get rid of all the square roots or all the cube roots or any roots that I have from the denominator. Okay, I can't have any radical symbols in the denominator. For this one, I've got to multiply it by itself. When I have a single term down here, just multiply it by itself for square roots. And when I do that, in the numerator, I'm going to have to distribute this thing. So in the numerator, root 3 times 5, again, stuff on the outside with stuff on the outside, stuff on the inside with stuff on the inside. So it's 5 root 3. When I do the root 3 times the root 2, they're each under the radical symbol, so it becomes a root 6. I'm allowed to multiply those. And now underneath, root 3 times root 3 is a root 9. Again, they're each under the radical, so I get to multiply those. And now I just simplify a little bit. This is a 5. That's an ugly looking 5. Let me try again. This is a 5 root 3 plus a root 6. I can't simplify that. But the square root of 9, that's just a 3. And that was the point of what I was doing. Now my denominator has something that's not a radical in it. Okay, I've got a rational number in my denominator, which is what I wanted. And that's why it's called rationalizing the denominator. Okay. If I look at the next one, I want to rationalize the denominator again. With a binomial, it's a little bit more complex. We have to multiply by the conjugate. Okay? And again, whatever I do to the denominator, I have to do to the numerator. I'm always multiplying by a form of 1. I just want to change what the fraction looks like. I don't want to change the value. Okay? In the numerator, I'm going to have to distribute or FOIL. In the denominator, I'm going to have to do the same thing. So in the numerator, when I distribute that 9, that's going to give me a 27 minus 9 root 5. When I distribute the negative root 5, I'm going to get a negative 3 root 5 plus the square root of 25. Again, I was just distributing. Distributed the first term, and then I distributed the second term. Okay? In the denominator, I'm going to do the same thing. I distribute that first 3, which is going to give me a 9 minus 3 root 5. And then I distribute the plus square root of 5. That's going to be a plus 3 root 5 minus the square root of 25. And again, I'm just distributing. I distributed this 3, and then I distributed the root 5. Okay? So I'm using my distributive property, or FOIL, first outside, inside, last. And now I combine like terms. I simplify some things. Right away, I can see that the square root of 25, each of those is going to reduce. It's going to simplify. This is going to be a 27 minus 9 root 5 minus 3 root 5 plus 5. Over in the denominator, I've got 9 minus 3 root 5 plus 3 root 5 minus 5. And now I'm just going to start combining some like terms here. In the numerator, these end ones are like terms, and then these middle ones are also like radical terms. In the denominator, it's the same thing. These end ones are like terms, these middle ones are like terms. So in the numerator, when I do the 27 plus the 5, that's going to give me a 32. When I do the negative 9 root 5 and a negative 3 root 5, that's a negative 12 root 5. In the denominator, what happens is these middle terms cancel out, okay, because one's positive, one's negative. And then I have 9 minus 5, which is a 4. But if I look at something like this guy, they're all divisible by 4. So when I simplify this thing, I can divide each piece by 4. The 32 divided by 4 is an 8. The negative 12 divided by 4 is a negative 3. So it just becomes this, okay? And that entire denominator goes away, all right?